Hello, welcome to Organic Chemistry Lectures delivered by Sheetal Bhatkurki. In this part of the lecture, I will be dealing with nucleophilic substitution reactions. At the end of the session, student will be able to identify the nucleophilic unimolecular and bimolecular substitution reaction. They will be able to predict the mechanism of SN1 and SN2 reaction, also comprehend the stereochemistry of SN1 and SN2 reaction. Nucleophilic substitution reactions. During 1930, Sir Christopher Ingold and Edward Hughes investigated substitution reaction in an effort to elucidate their mechanism. Based on their observation and observations of many other scientists, they proposed two different mechanisms for nucleophilic substitution reaction and suggested that each mechanism operate under a specific set of conditions. Substitution and elimination reactions are predominantly characteristic reactions of alkyl halides. When the halide of an alkyl halide is being substituted by a nucleophile, we call it as nucleophilic substitution reaction. Similarly, when a base is going to abstract the alkyl halide and lead to a formation of a pi bond is called as elimination reaction. This lecture will be dealt on the substitution reactions. Nucleophilic substitution is a fundamental class of reaction in which an electron-rich nucleophile selectively bonds with or attacks the positive or partially positive charge of an atom or a group of atom to replace the so-called leaving group. The positive or the partial positive atom is referred to as an electrophile. The whole molecular entity of which the electrophile and the leaving groups are part is usually called as substrate. Alkyl halide reacts with the nucleophiles and bases. Alkyl halides are polarized at the carbon halide bond, making the carbon electrophilic. In nature, the nucleophiles will replace the halide in CX bond of many alkyl halides, which reacts as a Lewis base. Nucleophiles that are Bronsted base produces elimination reaction, whereas nucleophiles that are Bronsted acids will produce a substitution reaction. Further, we classify nucleophilic substitution reaction based on their mechanism and chemical kinetics. They are classified as SN1, that is unimolecular, and SN2 bimolecular, where the notation S stands for substitution, N for nucleophile, because it is the nucleophile which is the incoming group after eliminating the halide group or the leaving group. Therefore, the notation N comes there. 1 represents that it is a unimolecular and 2 represents that it is a bimolecular. The reaction kinetics is expressed in the notation SN1 and SN2, 1 unimolecular, 2 bimolecular. Now, any alkyl halide which undergoes whether SN1 or SN2 depends upon the mechanism that predominantly is dependent on the following factors: the structure of alkyl halide, the reactivity of nucleophile, the concentration of the nucleophile, and the solvent in which the reaction is being carried out, which will be discussed in a short while. Let us start with the SN2 in the beginning. SN2 reaction. Herein SN2 represents that it is a bimolecular reaction. Notation itself is saying that it is a bimolecular reaction. It is a concerted mechanism, that means the bond formation and bond breaking is happening simultaneously there. There is no intermediate, but there is essentially a transition state. Energy required to break the bond is compensated by energy obtained during the formation of a bond. Configuration of the substituent of the product is inverted compared to the configuration of the reacting chiral alkyl halide. Therefore, stereochemistry leads in the inversion, and the rate of the reaction is dependent on the both the species, that is the substrate alkyl halide and the nucleophile. Therefore, it is a second order reaction and the term bimolecular comes. Example, methyl bromide reacts in presence of a hydroxy group, hydroxyl ion, forming a methyl alcohol and a bromide ion. Herein the mechanism says that there is a transition state but not an intermediate state. So, this is again a simple notation, table form representation, wherein the characteristics of SN2 mechanism are clearly indicated. Based on the backside attack of the nucleophile, the stereochemistry leads to the inversion of the configuration when compared to the reactant configuration. Mechanism. If we look into the mechanism, the halide is the good living group here and is ready to leave away, whereas the nucleophile is ready to attack the carbon. The moment the nucleophile is attacking the carbon bearing the halide, and the halide is ready to leave away, then both the nucleophile and the halide group will attain delta negative charge, whereas the carbon will attain the positive charge. If you look into the carbon is having now a 5 valency there. It is binding towards the nucleophile as well as towards the electrophile, and it is not, it wants to get rid of one of the bond, and that at that position the living group is it is ready to leave away and go, dragging out the electrons, thereby will leave away the substrate molecule, whereas the incoming nucleophile is going to form a new bond between the nucleophile and the carbon. So, in the mechanism it is very clear that it is a transition state which is seen there, and in the transition state both the nucleophile and the living group are held together, right. But the bond is not strong, one of the bond is going to be formed, that is carbon nucleophile is going to be formed, whereas carbon living group is going to be broken down. That is why the energy required to form carbon new bond is being compensated by the carbon living bond which is ready to break. Herein both the rate of nucleophilic substitution reaction, such as reaction of a methyl bromide as indicated with the hydroxide ion, depends upon the concentration of both the reagent, that is on the methyl bromide as well as the hydroxide ion. So, therefore, it is a bimolecular. It is rate is dependent on both the species, the reacting species and the nucleophilic species. So, any change in the concentration of any one of the substrate or the nucleophile is going to affect the rate of the reaction. If the rate of concentration of the methyl bromide in the reacting mixture is doubled, then definitely the rate of nucleophilic substitution reaction is going to be doubled. So, if I increase the concentration of hydroxide ion, then the rate of reaction is also going to be doubled. If I increase both, then the rate of reaction is quadruples. It is increased by 4 times. Therefore, rate is directly dependent on alkyl halide and the nucleophile. R is equal to K into alkyl halide into nucleophile concentrations, where K is the rate constant. Because of this, the reaction depends on concentration of both reactants and the both the reactants. The reaction is called as second order reaction, bimolecular reaction, 2 molecules. When the hydrogen of methyl bromides are successively replaced with the methyl group, the rate of reaction with a given nucleophile becomes progressively slower, which I will be indicating in the factors affecting the nucleophilic substitution reactions, SN2 particularly. So, the second example here, the tosyl group is associated. in the substrate, the tosyl group is also a good living group, wherein the acetate ion is going to be the nucleophile which is ready to attack the chiral carbon indicated with the asterisk there, leading to the formation of a inversion of configuration of the product by eliminating the tosyl group. Stereochemistry of the SN2 reaction, which is given by the Paul Walden. So, Paul Walden identified that the stereochemistry of the SN2 reaction leads to the inversion of configuration when compared to the reacting species. The carbon at which substitution occurs has inverted its configuration during the course of reaction. It is a concerted reaction wherein the bond formation and breaking are happening simultaneously. The incoming nucleophile will always attack the carbon from the back side but not from the front side, because from the front side is the more bulkier group, halide group, which is ready to leave away and go, whereas on the other side it is just a simple substitutions or hydrogens which are present there. Therefore, they give the space for the incoming nucleophile when compared to the halide group, and that is the reason why when the halide leaves away and go, the bond between the carbon and the nucleophile formed will be exactly in the opposite direction of the leaving group, and that is why it leads to the inversion of configuration. Backside attack leads to the inversion of configuration was well established by Walden experiments. If I start with the R substrate, for example, I have a R2 bromopentane, then the end product will be S2 pentanol, because the end product that I am going to get is an alcohol there. If I am using a hydroxide ion as a base, as a nucleophile there, then end up in product will be alcohol, and the configuration of the product will be exactly the reverse of the reactant. If I have started with R configuration, then I end up with the S configuration, vice versa. In the transition state, all the three bonds are in the same phase. The bond forming, the bond breaking are in the same phase. Therefore, they lead, once the bond leaving group has left and gone, then all of again it is going to acquire back a tetrahedral. So, from a tetrahedral it goes to a planar and then to a tetrahedral structure. Therefore, there is no change in any hybridization state and leads to the same hybridization with whatever we started, that is a sp3 hybridized carbon. Let us see some of the factors which are affecting SN2 reaction. Substrate, effect of substrate structure on the rate of SN2 reaction. If you look it into the methyl bromide, the rate of reaction of the methyl bromide is quite higher when compared to the tertiary bromide, tertiary alkyl bromide. Now, in SN2 reaction, it is the primary alkyl halide which is reacting at a very faster rate when compared to the tertiary alkyl halide. It is because the transition state does not involve any bond breaking or bond forming. It is concerted reaction happening simultaneously together there, and it is not an intermediate but a transition state. Therefore, the preferred alkyl halide would be the primary alkyl halide, which would undergo drastically SN2 reaction when compared to a tertiary alkyl halide. Even the energy profile diagram indicating the potential energy across the reaction coordinations indicates that the energy that is required for a methyl substrate would be much lesser. Activation energy required for a methyl substrate would be much lesser than a primary substrate, or a primary required would be much lesser when compared to secondary and tertiary substrates. Therefore, primary alkyl halide will undergo easily SN2 reaction when compared to secondary alkyl halide, and secondary alkyl halide compared to tertiary alkyl halide. In fact, tertiary alkyl halide are the most hindered to undergo SN2 reactions. Second factor is the leaving group. Halogen serves as a leaving group, and substitution and elimination process can occur only when a living group is present, or else the substitution or elimination becomes really difficult to undergo. Therefore, we need a good living group, and the living groups are the conjugate bases of a strong acid. Herein it indicates that the iodine, bromine, chlorine, fluorine, so on, when the acidity of this alkyl halides are increasing, so do their nature to leave away the substrate molecule is also going to be favored. Therefore, we see that the rate of reaction is much higher when there is a when the alkyl halide is a iodine compared to bromine compared to chlorine, whereas the least is the fluorine. We can also compare this to its basicity. Strongest basicity out of all of them, fluoride ion is the most strongest base and is least to go away as a living group. Therefore, is less susceptible when compared to iodine. The weaker the basicity of a group, the better is its living ability. Whereas, stronger the basicity of the living group of the alkyl halide, weaker is the living group. So, it loses its capacity to go away. Therefore, fluoride ions are least reactive when compared to the iodine. Relative leaving group abilities of the halide ions indicate that stable, that is weak base, are better leaving group. The halides have the following relative leaving abilities, that is iodine is the best leaving group when compared to bromine, bromine over chlorine, chlorine over the fluorine. So, out of all, the fluorine is the worst leaving group. Therefore, alkyl iodides are the most reactive of the alkyl halides and alkyl fluorides are the least reactive. In fact, the fluoride ion is such a strong base that alkyl fluoride essentially do not undergo SN2 reaction. Relative reactivity of alkyl halide in SN2 in that case will be alkyl iodide reacting at a very faster rate compared to alkyl bromide compared to alkyl chloride, and the least is the alkyl fluoride which will be hindered to undergo SN2 reaction. One more factor would be the high polarizability of the larger iodine atom causes it to react as if it were polar, even though on the basis of the electronegativity of an atom the bond is going to be non-polar. Therefore, iodine is much more reactive compared to the fluoride ion. The next factor is nature of nucleophile in an SN2 reaction. When we talk about the atoms or molecules that have lone pair of electrons, sometimes we call them bases and sometimes we call them nucleophile. What is the difference between a base and a nucleophile? Basicity is a measure of how well a compound, say a base, shares its lone pairs with a proton. The stronger the base, the better it shares its electron. Basicity is measured by an equilibrium constant, that is Ka, this acid dissociation constant, that indicates the tendency of a conjugate acid of a base to lose a proton. Whereas nucleophilicity is a measure of how readily a compound, say a nucleophile, is able to attack an electron deficient atom. Nucleophilicity is measured by rate constant K. In case of SN2 reaction, nucleophilicity is a measure of how readily nucleophile will attack an sp3 hybridized carbon which is equally bonded to a living group. When comparing molecules with the same attacking atom, there is a direct relation between basicity and nucleophilicity. Stronger bases are better nucleophiles. For example, a species with a negative charge is a stronger base and a better nucleophile than a species with the same attacking atom, that is neutral. Thus, hydroxide ion that is OH minus is a stronger base and a better nucleophile than the neutral molecule water. So on, the methoxide ion is a stronger base, a better nucleophile when compared to the methanol. When comparing molecule with attacking atom of an approximately the same size, the stronger bases are again the better nucleophile. The atom across the second row of the periodic table have approximately the same size. If the hydrogens are attached to the second row elements, the resulting compound have the relative acidities. Now, if we look into relative acid strength, then ammonia, water and hydrogen fluoride, then weakest acid is ammonia when compared to hydrogen fluoride there. Consecutively, the conjugate base have the following relative base strength and nucleophilicity. Herein we have indicated the base strength and the nucleophilicity. That is, NH2 minus is a strong base and the best nucleophile when compared to the fluoride ion F minus. Please note that the amide anion is the strongest base as well as the best nucleophile. When comparing molecule with attacking atom that are very different in size, another factor comes into play, and that is polarizability of the atom. Because the electrons are farther away in larger atom, they are not held as tightly as they can be, therefore move freely towards a positive charge. As a result, the electrons are able to overlap from far away with the orbital of the carbon as indicated in the figure here. This results in a greater degree of bonding in the transition state, making it more stable. Whether the greater polarizability of the larger atom makes up for their decreased basicity depends upon the condition under which the reaction is being carried out. So, if we will see here, an iodide ion is larger and more polarizable than a fluoride ion. Therefore, the relatively loose held electrons of the iodine ion can overlap from farther away with the orbital of the carbon undergoing nucleophilic attack. The tightly bound electrons of the fluoride ion cannot start to overlap until the atoms are close together. Now, when the reaction is carried out in gas phase, the direct relation between basicity and nucleophilicity is maintained. Stronger bases are still the best nucleophiles. If however the reaction is carried out in a protic solvent, meaning the solvent molecules have a hydrogen bonded to an oxygen or to a nitrogen, the relationship between basicity and nucleophilicity becomes inverted. Please note, it becomes inverted. The largest atom is the best nucleophile even though it is the weakest base. Therefore, iodine ion is the best nucleophile of the halide ion in a protic solvent. So, you can see the arrow indicating in the protic solvent. A protic solvent contains a hydrogen which is bonded to an oxygen or to a nitrogen. It is a hydrogen bond donor. The next factor is the solvent effect in SN2 reaction. Solvent plays a major role in nucleophilic substitution reaction, particularly in the SN2 reaction. In a protic solvent, when the smallest atom, the poorest nucleophile, even though it is the strongest base, it will not, how it will react in a polar solvent is a very important aspect that has to be taught. How does a protic solvent make stronger base, less nucleophilic in nature, is a question to be addressed. When a negatively charged species is placed in a protic solvent, the ions become solvated. Protic solvents are hydrogen bond donors. The solvent molecules arrange themselves so that their partial positive charged hydrogens point towards the negatively charged species. The interaction between the ion and the dipole of the protic solvent is called as ion dipole interaction. Because the solvent shields the nucleophile, at least one of the ion dipole interaction must be broken before the nucleophile can participate in a SN2 reaction. Weak base interact weakly with the protic solvent, whereas strong base interact more strongly because they are better at sharing their electrons. It is easier therefore to break the ion dipole interaction between an iodine ion and the solvent, iodine ion which is a weak base, and the solvent than between a fluoride ion which is a stronger base and the solvent. As a result, iodine ion is a better nucleophile than the fluoride ion in the protic solvent. So, increasing nucleophilic characteristics is also indicated there. So, recall what is polar protic solvent and what is polar aprotic solvent. Protic solvent example, any alcohol, water, acid, acetic acid, etc. are polar protic solvent, whereas polar aprotic solvents examples are acetone, DMF, DMSO, acetonitrile are the polar aprotic solvent. So, we can see here wherein it is indicated that in presence of a DMF and DMSO, right. So, DMSO and DMFO are clearly indicated. The delta negative is on the surface of the molecule and the delta positive is not very easily accessible in case of DMSO and DMFO. Whereas DMSO can solvate a cation better than it can solvate an ion. For example, fluoride ion would be a better nucleophile in a non-polar solvent than in a polar solvent because there would be no ion dipole interaction between the ion and the non-polar solvent. However, ionic compounds are insoluble in most non-polar solvent, but they can dissolve in aprotic polar solvent such as DMF and DMSO. An aprotic solvent, polar aprotic solvent is not a hydrogen donor because it does not have a hydrogen attached to an oxygen or to a nitrogen. So, there is no positively charged hydrogen to form ion dipole interaction. The molecules of aprotic polar solvents have a partially negative charge on their surface that can solvate cations, but the partial positive charge is in the inside of the molecule, which makes it less accessible. The relatively naked anion can be powerful nucleophile in aprotic polar solvent. Fluoride ion therefore is a better nucleophile in a DMSO than in its water. This question is frequently asked. Why fluoride ion is a better nucleophile in a polar aprotic solvent compared to polar protic solvent? So, the answer is whatever the explanation has been given, the answer would serve there. Nucleophilicity is also affected by steric effect in SN2 reactions. Base strength is relatively unaffected by steric effect because a base removes a relatively unhindered proton. The strength of a base depends on how well the base share its electron with the proton. Thus, tertiary butoxide ion is a stronger base than a ethoxide ion, since tertiary butanol, whose pK value accounts to 18, is a weaker acid than a ethanol whose pK value accounts to be at around 15.9. So, ethoxide ion is a better nucleophile, whereas when it comes to the base, then it is tertiary butoxide ion which is a stronger base. Steric effect on the other hand do not affect nucleophilicity. A bulk nucleophile cannot approach the backside of the carbon as easily as less sterically hindered nucleophile can. Thus, the bulk tertiary butoxide ion with its 3 methyl groups is a poor nucleophile than a ethoxide ion, even though it is a stronger base. Even though it is a stronger base. Again, many a times this question is always asked. Though tertiary butoxide is a stronger base, is not a good nucleophile. You need to justify your answer with the above reason. Some of the example of SN2 reaction. So you can see here nucleophilic substitution in the synthesis of two useful drugs. One is mambutanol and the other one is Prozac. So here we have the nucleophile. The amine lone pair electrons are nucleophilic in nature, whereas we have a dihalide here. So it is a ethylene dihalide which contains two leaving groups, that is two halides are the leaving groups. So both the halide ions are ready to leave away and go. Simultaneously, both the nitrogens are ready to attack the carbon or share its electron to the carbon, which is ready to cleave away the chloride ion. Thereby, a new bond is formed here. Two new bonds are formed between C and N. That is, construction of carbon-nitrogen bond is happened here. A new bond is formed between a carbon and a nitrogen, CN bond formation. In the second example, wherein iodine is the leaving group and the incoming nucleophile is again a amine there, primary amine as a nucleophile there, right. Again a CN bond has been formed in one step. Both the drugs are widely used in the industry. So in both the synthesis, the NH2 group serves as a neutral nucleophile to displace the halogen. The new bonds formed by the nucleophilic substitutions are shown in the red color in the products. Now, given to you is this example where I have R2 bromobutane which is reacting with the hydroxide ion. So what would be the end product? Definitely it would be an alcohol, but the end product would be with the S configuration, as we know what is Walden invention now. Yes, so you can see that it is S-butanol. Few more examples wherein different kinds of nucleophiles are attacking the alkyl halides. Hydroxide ion, SH minus, which is a stronger nucleophilic in nature, NH2 minus, again a stronger nucleophile, a cyano compound, that is C triple bond N, is again a nucleophilic in nature. With this, let us move on to SN1 reaction. SN1 reaction, the notation indicates that it is a nucleophilic substitution unimolecular reaction. Rate of the reaction depends only on one of the reactant, and that is it is dependent only on the substrate but not the nucleophile. That means if I increase the concentration of substrate, then the rate of SN1 reaction is going to be increasing, and if I increase the concentration of the nucleophile, there is no effect on the increase in the rate of reaction, because SN1 is independent of the nucleophilic concentration. Rate of reaction with respect to SN1 is independent of the nucleophilic concentration. Therefore, it only depends upon the substrate, and if I increase or decrease the substrate concentration, then rate of reaction is also going to be either increasing or decreasing respectively. Highly substituted reactants will undergo SN1 reaction. If you observe, the less substituted alkyl halide underwent SN2 reaction, whereas highly substituted alkyl halide are ready to undergo SN1 reaction. Characteristics of SN1 reaction. It undergoes through a first order kinetics because rate is only dependent on the substrate, whereas not dependent on the nucleophile. It is not a concerted reaction unlike your SN2. It is a two-step mechanism where the leaving group departs and the nucleophile approaches afterwards. It is not going to be happening simultaneously unlike your SN2 reaction. Stereochemistry, it is leading to the racemization. That means there is retention of configuration plus a small amount of inversion also happening. Therefore, we end up into a racemic mixture in SN1. Alkyl halide, the more substituted alkyl halide reacts at a very faster rate when compared to the SN2 reaction, in which less substituted alkyl halide will undergo SN2 reaction. Let us look into the mechanism of SN1 reaction. In SN1 reaction, it is a two-step mechanism. The first step is the generation of a carbocation. A carbocation has to be formed there. When the leaving group is ready to leave away and go, the formed ion is a carbocation, which is a stable carbocation. If required, it do undergo rearrangement. In the second step, the incoming nucleophile will share its electron to the formed carbocation. The first step, that is the formation of a carbocation where the leaving group is ready to leave away and go, it depends upon the leaving group, how best is the leaving group, right. So, first step is the slow step and is the rate determining step, because the concentration of the alkyl halide is what is going to determine the rate of reaction. Therefore, it is the first step, the slow step, which is the rate determining step. Whereas nucleophilic attack on the carbocation leads to the formation of a new bond, and the new bond formed can be, depending upon what is the nucleophile, it can be carbon oxygen, carbon nitrogen, carbon sulfur, etc. This is a Lewis acid base reaction. The nucleophile is the Lewis base and the carbocation is the Lewis acid. Compared to step 1, step 2 is faster because no bond are broken and no bonds is been formed there. No bond is broken there, but one bond is formed there. Sorry, one bond is been formed there, and that bond can be CO, CN, CS. Stereochemistry of SN1 reaction. After losing the leaving group in the step 1, where they generate a carbocation, the carbocation formed is a planar, is planar in structure. So, we started with a tetrahedral structure and attained a carbocation which is a planar, which is in planar. So, planar carbocation which is achiral in nature, right. In step 2, when a nucleophile share its electron, when it is ready to share its electrons, it can come from either side, from the front side or from the back side. Because there is no preference of nucleophilic attack either of the directions, so equal amount of two enantiomers will be formed, wherein we call it as a racemic mixture. So, racemization has occurred. If it attacks from the back side or opposite side of the leaving group, then it would be inversion, and if it attacks from the same side where the leaving group has left and gone, then it would lead to the retention of the configuration, and that is the reason why we end up into a racemic mixture. Now, it also depends upon what are the R groups. If more the bulkier the R groups, then the incoming nucleophile would try to avoid from that position where the more bulkier group is been positioned. So, this is the stereochemistry, which is again saying that how a inverted configuration is obtained. So, you can see here when the leaving group is here on my right hand side when I am standing towards you, and the incoming nucleophile is from the left hand side. Therefore, it leads to the inversion, whereas if the incoming nucleophile is also from the same direction from where the leaving group is going, leaving away and going, then it leads to the retention. Therefore, we end up into a racemic mixture. Similarly, the factors which affected SN2 are also going to affect SN1, but in a different fashion. Let us see that. Factors affecting SN1 reaction. Relative rate of SN1 reaction in alkyl bromides. So, if you see tertiary alkyl bromide relative rate is much higher when compared to the primary alkyl halide or methyl halides. Now, why is the tertiary alkyl halide is going to be more reactive when compared to primary alkyl halide? Let us step back little. The first step that is going to be formed in the SN1 reaction is a carbocation. And recall that when we talk about the stability of a carbocation, it is the tertiary tertiary carbocation which is more stable when compared to secondary over the primary and primary over the methyl cation. Therefore, when a cation is formed in a reaction course, it would rather try to form a more stable carbocation. So do when I take a tertiary alkyl halide, with the elimination of the halide, a more stable tertiary alkyl carbocation would be formed there. Tertiary carbocation formed is much more stable there. Because of the plus inductive effect of the 3 alkyl groups, it would be much stable. Therefore, it would lead to a most reactive alkyl halide with respect to SN1 reaction. Second factor depends upon the leaving group. But leaving group will help us to predict whether there is SN1 or SN2 reaction mechanism happening in the substrate. Leaving group is a very important factor for us, right? A better leaving group increases the rate of both SN1 reaction as well as in SN2 reaction. In SN1 as well as in SN2, the rate of reaction was dependent on the alkyl halide. In SN2 it is dependent even on the nucleophile, whereas in SN1 it is solely dependent on the alkyl halide. So, it depends upon the leaving group. If I have a more easy leaving group, the leaving group is happily ready to leave away the substrate molecule, then it will be little faster when compared to a hindered leaving group which is not ready to leave away the alkyl halide. Therefore, alkyl leaving group plays an important role in SN1 to determine whether it is a good leaving group or a bad leaving group or a moderate leaving group. Based on that, I can say how fast or how easiness is the SN1 reaction. Here, tertiary alkyl halides are more reactive than the secondary alkyl halide, which are more reactive than the primary alkyl halide. This is because the more substituted the carbocation, the more stable it is, and therefore the easier it is going to be formed. But how do we rank the relative reactivity of a series of alkyl halide with different leaving groups that dissociate to form the same carbocation? As in the case of SN2 reaction, there is a direct relationship between the basicity and the leaving group ability. Even in the SN1, this plays an important point for us. The weaker the base, the less tightly it is bonded to the carbon and easier it is to break the carbon halogen bond. As a result, alkyl iodide is the most reactive and alkyl fluoride is the least reactive of alkyl halide in both SN1 as well as in SN2 reaction. I repeat, weaker the base, less tightly it is bonded to the carbon and more easy it is to break the carbon halogen bond. As a result, an alkyl iodide is more stable or more reactive and an alkyl fluoride is the least reactive of the series of alkyl halide in both SN1 as well as SN2 reactions. Nucleophile. The nucleophile reacts with the carbocation that is formed in the rate determining step of an SN1 reaction. Because nucleophile comes into play after the rate determining step, the reactivity of nucleophile has no much effect on the rate of SN1 reaction. That means the nature and the concentration of nucleophile is not going to affect to a greater extent in SN1 reaction. Whereas in SN2 definitely it is going to be affecting. Effect of solvent on the rate of ionization of tertiary butyl chloride. If you take an example here, it is a tertiary butyl chloride and the solvent. You can see that there are different solvents here from all are polar solvents, protic and polar aprotic solvent. Water, the rate of reaction is 40, whereas if I take acetone, the rate of reaction is relatively very less. This means that the SN1 reaction more preferred is the polar protic solvent compared to polar aprotic solvent. Competition between SN1 and SN2. If we compare between SN1 and SN2, SN2 is a concerted reaction whereas SN1 is a two-step reaction. Here the rate of the reaction is dependent on both the nucleophile and the substrate, whereas in SN1 it is only dependent on the substrate. It is a transition state which is occurring in SN2, whereas a carbocation is going to be formed in the first step. Generation of carbocation is what's seen in the mechanism of SN1. The stereochemistry of the product with respect to SN2 is going to be inversion, that is exactly the reverse configuration is going to be obtained, whereas in SN1 it is the racemic mixture that is going to be obtained, that is retention with the inversion is what is going to be obtained in the stereochemistry of the product. Order of reactivity, methyl and the primary alkyl halide reacts at a much faster rate in SN2 reaction compared to the tertiary alkyl halides which reacts at a much faster rate in SN1 reaction. So, substitutions if we see, then methyl and primary alkyl halide would undergo only SN2, whereas vinyl and aryl halides will neither undergo SN1 nor undergo SN2 reactions. Secondary alkyl halide can undergo SN1 and SN2, therefore the factors are very important for us when it is a secondary alkyl halide. For example, if I have a very good nucleophile, then it would prefer to undergo by SN2 mechanism. But if I have a polar solvent, then it would prefer to undergo by SN1 mechanism. So, with respect to secondary alkyl halide, lot of tricky things can be there. So, we need to ensure the factors, we need to see all the 4 or 5 factors which we discussed, right. Similarly, with the primary, secondary benzylic as well as primary, secondary allylic halides also, SN1 and SN2 both can be operated, which solely depends upon what is the condition that we are going to prefer. Tertiary alkyl will undergo only the SN1 reaction. So do benzylic and allylic tertiary halides will undergo only the SN1 reaction. So quickly let us recall, 4 factors are relevant in predicting whether a given reaction is likely to proceed in SN1 or SN2. Increasing the alkyl substitution favors the SN1, whereas decreasing the alkyl substitution on the alkyl halide will favor SN2, right. Strong nucleophile will favor SN2 reaction. Remember, as in the rate of reaction with respect to SN2 is dependent equally on the nucleophile. So we need a stronger nucleophile which would help us to lead to a formation of a rate of reaction is going to be much faster with respect to SN2 reaction. And second factor is the nucleophile is not going to be involved in your SN1 reaction. So it does not matter how strong or what is the concentration of this nucleophile in your SN1 reaction. Strong nucleophile will favor SN2 reaction, weak nucleophile may favor SN1 reaction, right. Solvent, polar protic solvents will more favor SN1 reaction because ionic intermediate is formed there which will help it by the which is going to be stabilized by the solvation, whereas polar aprotic solvent is going to be favoring SN2 reaction because nucleophiles are not well solvated and therefore are more nucleophilic in nature. Therefore, we do not require polar protic solvent, but polar aprotic solvent is required. Now factors, all the factors has been discussed. So with this I would like to end up my session today. Before I end up, summary, nucleophile notation, please be sure with the notation 1 and 2. 1 is unimolecular, 2 is bimolecular. 1 unimolecular because rate is only dependent on alkyl halide or the substrate. 2 because the rate is dependent on the substrate as well as the nucleophile. What are the substrate? SN1 tertiary, SN2 primary. Solvent, SN1 is generally enhanced by polar solvent, SN2 by polar aprotic solvent. SN1 requires good Leving group because it is the rate determining step. So if we have a good Leving group, then readily we can reduce the slowness of that step. SN2 is the not much enhanced with the leaving group, right? Not as important, but enhances the reaction in case of SN2 also. Results, if you look into kinetics, first order with respect to SN1, second order with respect to SN2, stereochemistry, SN1 retention of configuration and inversion both seen, therefore racemic mixture, SN2 only inversion. Rearrangement, yes, rearrangement is possible with respect to SN1 where the carbocation is going to be formed, whereas in SN2 it is the transition state, therefore no rearrangement is going to be possible there. With this, I would like to end this session. Thank you.